Okay, we're looking at liquid pressure here in this problem, and I'm going to tie this into a classic novel, 20,000 Leagues Under the Sea, and we're going to figure out how much water pressure did the Nautilus have to withstand when it was 2,000 meters under the surface. So, figure out pressure. We have to take our pressure equation, which will tell us that if we take the density of the water that it's in, multiply it by force of gravity and how deep it is, that will simply give us pressure that the Nautilus is undergoing. So pressure is equal to the density of the water is given to us at 1,025, and that's kilogram per meter cubed. Okay. Force of gravity 9.8 meters per second squared. And the distance that's under the water is 2,000 meters. Please note that our units are all matching up. In other words, we're using kilograms, meters, and seconds in this. Multiply that out, and you'll get something in the order of magnitude 2 times 10 to the 7th pascals.
Okay, so now we have our pressure value given. The second part of this says calculate the force exerted on a 0.85 square meter porthole. And again, remember that pressure can also be defined as a ratio of force per area. So we have a pressure value that has been calculated at 2 times 10 to the 7th pascals. We are looking for the force value. They've given us an area. And so through some simple algebra then, we can find that the force that would need to be withstood by this porthole here is actually 1.7 times 10 to the 7th newtons. So that would be the force exerted by the water. Hey everyone, here's your Sioux Falls physics teachers again, looking more with liquid pressure. Here we have a submarine and it is 1,200 meters under the surface. We're going to be calculating two different types of pressure, the gauge pressure and the absolute pressure. So first of all, we'll start with the gauge pressure. And remember that when we say gauge, in reality what we really mean is just the pressure that is caused by the liquid itself. So this part would be represented in our equation by the density times gravity times height portion. And all of these quantities have been given to us in the problem. 1,025 for the density. Gravity is at 9.8. And the height would represent the depth below the surface in this case, which is the 1,200 meters. Solving that out, we get a pressure of 1.2 times 10 to the 7th pascals. And again, this portion just represents the gauge pressure in this situation.
Okay, the second part of the problem says to find the absolute pressure. So let's talk here for a second. What is different about absolute pressure versus the gauge pressure? In calculating the absolute pressure, we now need to consider all pressures that are acting upon the submarine. So now we need to include the atmospheric pressure that would also be on top of this vessel. So we're going to change a little bit here. Our pressure equation now needs to include the atmospheric pressure in addition to the pressure that the water puts on the vessel. Okay? The gauge pressure was the pressure that the liquid or that the water put on there. So we've already figured that out. We know that that's 1.2 times 10 to the 7th pascals. Okay. We need to figure out what the atmospheric pressure is. Well, that's just a given value at 1.013 times 10 to the 5th pascals, and so I will add that to 1.2 times 10 to the 7th pascals. Okay, adding those two values together, we notice that our total pressure is now 1.21 times 10 to the 7th pascals. Not that much different for our absolute pressure compared to our gauge pressure. And the reason being is that when you're 1,200 meters under the surface of the ocean, most of your pressure, if not all of it really, is coming from the water. The atmospheric pressure is very minimal when you're that far under the surface.
Your Sioux Falls physics teachers here again today looking at the buoyant force. We have a rock with a given mass and volume. It's attached to a spring scale and submerged in a tank of water. The first question asks, what is the reading on the spring scale? So as usual, we want to start with a free body diagram. Notice that the rock, even when it is underwater, still has an amount of weight pulling down. We also know then that because it is submerged, it will have a certain amount of buoyant force pushing upwards. And then finally, in addition to that, the scale itself is also pulling upwards. So as we can see then, because it is at rest at the current time, the scale and the buoyant force together will cancel out the weight. And so the first thing we want to do then is figure out how much buoyant force we have. Our equation for buoyant force is density times gravity times volume. And remember that in this case, the density represents the density of the water. So it's the density of the liquid that is causing the buoyant force. And assuming this is normal water, that would be a density of 1,000 kilograms per cubic meter multiplied times gravity of 9.8. And then finally times the volume of the rock, 0.006 cubic meters. And again, notice our labels would all cancel out. We would have cubic meters canceling out, and we would be left with kilogram meters per second squared, or newtons. By doing this, then, we could figure out the buoyant force on the rock. And we find that we have 58.8 newtons of buoyant force. So now if we take a look at our free body diagram, we can say that the weight is equal to the buoyant force plus the force from the spring scale. Our weight can be found by taking our mass of 26.8 kilograms multiplying times 9.8. Our buoyant force we found was 58.8 newtons. And if we do the algebra on that, we find that the force exerted on the scale will be approximately 204 newtons.
Okay, part B of this problem says then to determine the acceleration of the rock if it's released from the spring scale. So again, let's go back to our free body diagram here. If we no longer have the rock attached to the spring scale, the forces then that are acting upon it, again, are the weight pulling down and the buoyant force pushing up. We will no longer have the spring scale acting as a force. So we know that the net force that acts on an object is equal to its mass times its acceleration. So to find the acceleration, we're going to use this equation. First of all, to figure out the net force that's acting on this, okay, that will simply be the weight of the rock minus that buoyant force, okay. So if I calculate that, the F net, the weight of the rock, again, was 26.8 kilograms multiplied by the 9.8, okay, minus the buoyant force, which we calculated from part 1 at 58.8 newtons. That will give us a net force of approximately 204 newtons. What we had already got in part 1. Now, to figure out the acceleration, I'll put my net force, 204 newtons, equal to the mass of the rock, 26.8 kilograms, and multiplied by acceleration. Do a little division, and I'll get an acceleration value of 7.6 meters per second squared. Okay, the Sioux Falls physics teachers are back again. Work done by buoyant force. So we have a baseball that's released, goes into a swimming pool, goes down to a depth of 1.4 meters before it stops and then starts to float back to the surface. We want to determine the volume of the baseball. To start out with, we need to figure out the force that is done by the water, the buoyant force. Once we know that, then that will let us calculate the volume of the baseball. So let's draw a diagram of the situation here. We know a baseball is being released, and it says that it is being released at 0.5 meters above the surface of the water. Okay. Now, once it goes into the water, it then goes to a depth of 1.4 meters below the surface. Before it stops and starts to come back up. What we want to look at here is looking at energy and how energy is conserved in this situation. And an easy way to consider this would be to, rather than setting the zero level being the depth or the surface of the water, to rather instead consider our 0 point being the position where the ball finally stops moving. Okay? If that is the case, then we're going to have a situation that will look like this. We will look at the potential energy that we start with, plus the kinetic energy that we start with, plus some work that is going to be done. Now, where is that work going to be done? The work will be done as a result of that buoyant force of the water, which is going to be slowing down the baseball. That will then have to equal our potential energy plus our kinetic energy at the end, or at our 0 point. Okay. Now, why did we want to set our 0 point at that 1.4 meter depth below the surface? Well, that will then effectively make our potential energy 0 at the end because it will have no height. And also our kinetic energy at the end will also be 0 because it's not moving at that point. What about the left side of the equation then? What would be our potential energy as we start this? Remember, we are releasing the ball a half a meter above the water, and then it's going to fall another 1.4 meters. So potential energy is the mass multiplied by g times the height. Okay. We know the kinetic energy is 1/2 mv squared. And we know that the work that's being done is going to be representative of the buoyant force multiplied by the distance that that work is done over, or that force is applied over. Work is force times distance. So the mass of the baseball is 150 grams, so 0.15 kilograms, multiplied by 9.8 for G. And the height would end up in this case being 1.9 meters. Remember, we've set our zero line at the 1.4 meter depth below the water, so we have to add the 0.5 and the 1.4. That would be representing